Hello. Welcome to CS325. Modeling and Simulation Theory. Lecture 6, Systems Modeling. Analysis and Operations Research. This lecture will focus on queuing simulations, functional models, constraint models, and spatial models. Before that, let's review first the story on the text-based conceptual model. The system will be placed on a two-lane highway with sufficient space to construct double bypass lanes for 500 meter. The bypass lanes will contain a two-lane toll area that will provide cash and credit toll payment and change on a 24-hour basis. The lanes of the main highway will contain our new E-ZPass electronic toll collection capability. Drivers signed up for the E-ZPass system will remain on accounts will automatically be credited as the cars pass by using the constructed highway sensors. The bypass toll lanes will have sufficient space for non-E-ZPass users to queue while paying the toll. We believe that E-ZPass will be a significant disadvantage to local drivers and our subscription accounts will quickly rise due to the obvious convenience. An early advertising campaign will ensure significant enrollment before the system comes online. Now let's discuss queuing simulations. If traffic is busy enough and there are too many drivers not using E-ZPass, the queue of cars at the toll booth could potentially get so long that traffic on the main highway becomes disrupted. We need to answer the questions on how long will the queue get during various times of the day and various days of the year. And what is the trade-off in loss of revenue versus length of ramp if we have to stop charging tolls when the traffic volume is too high for the pay toll booths to operate safely? Let's tackle the question of queue length by first examining data about the flow of traffic at the proposed site of the E-ZPass system. Our data collection team installed traffic counters for several months and found that the traffic during the day before the Thanksgiving holiday was by far the busiest day of the year. Thanksgiving Day holiday was by far the busiest day of the year. The executives decided that this was a statistical outlier that would have to be handled by intermittent no-toll collection periods. However, they noted that the next busiest day of the year was equivalent to a sustained weekday rush hour interval and would like a weekday analysis as well as a heavy rush hour load analysis. In Figure 6.8, the model shows the two-lane toll booth with two separate queues, which we assume to be serviced by two separate toll booth cashiers. For simplicity, our model simulates just one queue and server combination and the server is the toll booth operator for the indicated lane. The service time per car will be 2 minutes plus or minus an error of a few seconds provided by a normal distribution with a mean of 3 seconds and a standard deviation of 4.5. The traffic rates per 2-hour period and the inverse of these will translate to inter-arrival or the length of time between cars averages for our random draws from an exponential distribution. For example, if the traffic rate is 50 cars per hour, this translates to 1/50 which is equal to 0.02 hour or 1.2 minutes between cars, but since we have two lanes, we can divide the rate in two to get 1/25 which equal to 0.04 hour or 2.4 minutes between cars entering into one lane of the toll ramp. Therefore, our inter-arrival distribution is exponential with a mean of 2.4. Arrival event signals the entry of the next car into this queuing simulation aspect of the E-ZPass system. A new entity arriving will enter the queue if one already exists or immediately begin being serviced. An entity or car that has completed paying the toll will then depart the system, causing a new departure to be scheduled for the next entity beginning service. Not shown in the GUR is the fact that if there are no cars already in the system, a new arrival will not be queued but rather will go straight into service and therefore would also trigger a departure to be scheduled in addition to the scheduling of the next arrival. All events are tagged with a time stamp, which indicates when the event should occur in time. The event queue in the GUR shows that the arrival event A9 will occur at time 2:15, while the departure event D1 will occur at time 2:16. The departure time for D1 minus the arrival time A1 will tell us how much time car number 1 spent in the system. Since we are interested in the length of the queue, we will keep track over the entire day of how many cars enter the system and how many cars leave the system. The difference between these will indicate the queue length at a particular point was in time. By making further assumptions such as an exponential service time instead of a normal distribution, the approximate average length of the queue is 4.2 cars using a relatively simple queuing theory formula. The traffic rates change about every 2 hours, while the queuing theory equations are for theoretically infinite runs. Our queuing simulation model will provide better estimates that are tailored to the easy pass system parameters. After having determined the queue length, we note that we also need to accommodate enough space for deceleration as cars come off the main highway and onto the toll ramp where they will come to a stop. Now let's move to functional models. Knowing the average and maximum queue lengths for the toll ramp, we need to know that there is adequate stopping distance between the end of the queue and a car that has exited the main highway. Given the speed limit for this stretch of road and assuming good weather conditions that permit traveling at the speed limit, we need to answer the question: what is the stopping distance that is needed? The stopping distance is given as d and the initial velocity as a vehicle enters the toll ramp is v sub 0. The resistive force due to friction after brakes are applied is given as F sub F, which is equal to the coefficient of friction multiplied by the force which is applied by the weight of the vehicle. In figure 6.9, F sub F is equal to mu times m, times g, where m is mass, and g is the acceleration due to gravity. Since this force is applied in the opposite direction to the movement of the car, the result is actually a deceleration. The well-known equations A, which is equal to dv over dt, and v, which is dx over dt, indicate that acceleration is the derivative of velocity with respect to time, and velocity is the derivative of distance with respect to time. In figure 6.10, we create a block model with these relationships. A block model is a connected network of components that have transfer functions with different capabilities depending on the type of component a block or connectable icon is representing. The integrator blocks shown by the integration symbol provides the derivative relationships described by the physics-based equations above. Besides the integrator blocks, the GUR also shows a constant block that will output the constant deceleration value obtained by multiplying the coefficient of friction with the value for g, which is equal to 9.8 meter per second squared. If we assume that the friction coefficient on a nice weather day is 0.75, the deceleration A sub f will be equal to mu times g, which is equal to 0.75 times 9.8 or 7.35 meters per second squared. Also, based on the speed limit, the initial velocity v sub 0 will be approximately 25 meters per second. Conjuring our block model with these initial values and simulating for 5 seconds, we get the following results. Figure 6.11 shows two plots in which both horizontal axes display time. The plot on the left in figure 6.11 shows the output of the middle velocity block in the block model. Note that the plot starts initially from 25 meters per second on the vertical axis and consistently decreases until zero velocity. This deceleration occurs in about 3.4 seconds. The right plot is the output of the distance block in the block model. The vertical axis here is distance traveled in meters. So, over the same amount of time, it can be seen that the car travels about 42.5 meters, which answers our question about the stopping distance needed for cars entering the toll ramp from the main highway. Now let's move to constraint models. Constraint models are similar to functional models except that the directed nature of the connected components, as can be seen from the block model, is less important than the physics-based relationships among system components and the balancing of those physical properties. Here we note that conservation of energy is involved. The law of conservation of energy tells us that the total energy in a closed system remains the same, although some of the energy may be transferred from one form of energy to another. Such a concept is useful when looking at multi-domain systems, as different forms of energy are likely to involve elements where different physics-based equations apply. For instance, a light bulb transforms electrical energy into light and heat energy. All three domains have their own energy equations but can be balanced to show the transfer and relationships necessary to perform a proper analysis of the system. Our easy pass stopping distance problem can be approached in this manner. First, the kinetic energy associated with the moving car is equal to 1/2 times m, times v sub 2, where m is mass and v is velocity. When the car comes to a complete stop, its velocity is 0 and so this form of energy goes to 0. Much of this energy loss is dissipated as heat. The friction force F sub F is equal to mu times m, times g, so our constraint model is 1/2 m times v squared equal to F sub F times d. Or 1/2 times v squared minus mu times m, times g, times d, which is equal to 0. Solving for distance we get 1/2 times v squared over mu times g. The initial velocity we used for our car was 25 meters per second, and so 1/2 of the velocity sub 2 times 2 is equal to half of 625 or 312.5. From before, we know mu times g to be equal to 7.35 meters per second squared. So, our stopping distance d is equal to 312.5 over 7.35 is equal to 42.517 meter, which is equivalent to what we obtained using our functional block model. The power associated with this energy transfer is equal to energy transferred per unit time. Assuming a 1088 kg vehicle and remembering that the vehicle was stopped in approximately 3.4 seconds, the power associated with this system is 1088 times 312.5 over 3.4 is 100,000 joules per second or 100 kilowatts. In our easy pass system example, these relationships were kept within a single domain, but if we were using a motor to crank a generator to in turn create electricity that powers a lantern where our objective was to measure the heat from the lantern, these relationships would span many domains. The energy balance across the domains would create constraints that enable the needed analyses. Lastly, the spatial models. Spatial models are multi-element models where either the spaces in the system are the elements or the entities within the spaces are the elements. An additional trait of these models is that elements are treated in a somewhat regularized manner so that rules of updating spaces or the behavior of entities within the spaces are uniform for many, if not all, of the elements. A common modeling method in which the space is the element that is focused on is the cellular automaton. Cellular automata are regularized matrices of cells in which each cell has the same set of rules to apply in order to update the information within itself. A given cell may also utilize the current information in neighboring cells but may not change information in other cells. The game of life is a popular implementation associated with cellular automata. The rules are very simple. First, cell is either alive or dead. Second, cell stays alive if there are 2 or 3 other live cells around it. Third, if there are less than 2 live cells around, it dies of loneliness. Fourth, if there are more than 3 live cells around, it dies of overcrowding. Lastly, if a cell is dead and there are 3 live cells around, it becomes alive. The cells in the grid have a different color depending on whether they are alive or dead. As the rules are applied, the colors in the grid change and shift, sometimes dramatically and sometimes none at all. Depending on the initial marking of alive and dead cells, various patterns can emerge that could be used to model real-life phenomena. For our easy pass system, we will draw upon rules governing the transfer of heat using a different spatial model but also dividing up our system into elements. The executives are concerned that the coefficient of friction we are using will change due to the heat from the car tires when pulling off onto the toll ramp and applying brakes. We will assume that brakes are applied when the car is traveling in one direction and that the maximum heat is transferred at the moment that brakes are applied. We will look at a small one-dimensional segment of road and treat it as an isolated and homogeneous section of material. Figure 6.12 is our section of road where a tire has applied 1 unit of heat to the center of the section. The assumed uniform material will conduct heat in both directions, and so we want to study how this heat will dissipate over time to eventually determine based on time between vehicle arrivals whether or not this heat will linger to affect a change to our coefficient of friction used in the previous evaluations. We divided our material into 9 equal parts as shown in the GUR. So this is indeed a multi-element model, and because we will use a partial differential equation. The heat equation. To model the relationships between elements, this is also a Knight element model. The heat partial differential equation, PDE, specifies the rate of temperature change with respect to time and position, while ordinary differential equations define rates of change only with respect to time. As mentioned in the beginning of this section, cellular automata are spatial models where the spaces in the system are the elements that are treated with regularized rules of updating the spaces. Spatial models also focus on systems where the entities within the spaces are the elements with regularized behavior for updating the states of entities. Multi-agent modeling is a common modeling method that focuses on the entities within the space. Probably the most interesting characteristic of agents is their autonomous nature. Their rules of behavior allow them to know when and how to act on the system as necessary. Multi-agent models are used extensively in modeling human behavior, such as in crowd models or in military battlefield scenarios, where a mathematical model of the whole system would be too complex with too many simplifications needed. For our easy pass system, agents could obviously be the cars themselves, but they could also be the drivers as well. In fact, depending on the question being asked, our entity-based multi-element easy pass spatial model could include other agents such as the camera, sensor, toll booth operators, and so on.